Lab 2 presentation Drop the Charges. The purpose of this lab was to find out the charge of the unrolling tape and how many electrons were gained or lost by using the Coulomb's law and experimental skills. First, as an overview of what a charge means, it is an electrical property that some particles have. For example, electrons have a negative elementary charge, whereas protons have a positive charge. Objects can also be neutral, especially if they have not been rubbed against anything. For example, atoms are electrically neutral. For this lab, we are using tape, which usually gets attracted to your hand because of polarization. The tape was attached to another piece of tape in the tape roll. Therefore, it is charged by the time that you rip it and touch it. The hands are most likely sweaty, which creates some type of electric pulse that induce or attract the charges of the tape to your hand. These particles, positive or negative, arrange across the surface from one side of your hand to the other one. Thereby, the opposite charges attract and the same charges repel each other. This is possible because of polarization. After completing the methodology and calculation, we got our results. We determined that both of our tape were positive because we charged a balloon by rubbing it to human hair. Due to the triboelectric series charge, we know that human hair is at the top of the chart, meaning that it's likely to lose electrons and become positive, whereas silicone rubber is at the bottom, which means that it becomes more negative by gaining electrons. And we know that most balloons are made of rubber. When we charge the tape with the base tape and it becomes charged, we move it closer to the balloon that was now negative and it attracted to the balloon, which means that they were opposite charge, this making the tape positive. But this also indicated that the base tape that it was rubbed against was negative since it technically took some electrons from the tape. After making all the calculations, we got that the charge of the tape was 2.454 tenths to the negative 8 coulombs, and the amount of electron deficiency since it lost electrons on tape B was 1.467 tenths to the positive 11. The fraction on atoms to give up electrons of the tape was 1.544 tenths to the negative 5, which means the fraction of the electrons lost divided by the electrons that were first found on the surface of the tape. Before calculating our results, we first determined the maximum and minimum amount of electrons that could be transferred at the lower and upper bound surface of the tape. The minimum was 1 electron, which is transferred to 1.67 10 to the negative 19 coulombs, and the maximum charge, which is the upper bound, was 0.35 10 to the negative 3 coulombs. Since the tape is an insulator, the charges do not move freely. All atoms are found on one particle, as we can see on this picture right here. By measuring the length and width of the tape, which was 20 centimeters for the length and 1.9 centimeters for the width, we then calculated the amount of atoms that could fit in that length. Our results, as we saw on the previous slide, were within the lower and upper bound. Our charge was within this charge in coulombs, meaning that the amount of electrons that the tape lost were pretty accurate. In addition, we also made some assumptions to calculate the mass and charges of the tape. The first one being that both charges on the tape are the same in size and magnitude. The second, that the deficiency, because it lost electrons, charges are concentrated on one part of the center of the tape, as I mentioned in the picture, and that the tape experiences gravity on air, which is 9.8 meters second square, since the experiment was performed in a physics classroom, which is on Earth. We determined the charges to then calculate the value for Q, which is the charge. Following understanding the forces acting on the tape, we make it easier to solve for the charge of the tape by using Newton's second law. The forces acting on tape B, which is the tape at the top, are gravity pointing down and the electric force pointing up. It points up because it's experiencing a repulsion from tape A, which is found at the bottom. Applying Newton's second law, we equal both forces to mass time acceleration, but the acceleration is actually zero because when the tape A moves up, it balances the gravity from tape B off. It's like they cancel each other out. Hence, the net forces acting on tape B are also zero. The net force is zero. Since we know it is a positive charge, its electric field will point radially outward. To solve for Q symbolically, we just move mg, which is the gravitational force, to the right, and then multiply it by the distance squared and divide it by Coulomb's constant, and take the square root. Distance is the same as small r, and it should be outside the square root in order to get the right result number. The values that we know so far are the Coulomb constants and gravitational force, but we still don't know the mass or the distance between the tapes when they experience repulsion. The setup for this experiment is simple. The trickiest part is to put the tapes in the lever support without touching it, as you will be able to see in this video. It is important to only touch the tape at its end, so no electrons are transferred between you and the tape. We also did this experiment closer to the humidifier in the room to avoid charges getting lost by the moist in the air, which is a great conductor. As you can see in the video, the tapes get charged by quickly ripping them off from the base tape. Then we check each charge by getting it closer to the balloon, and that's how we found out that the tapes were positive. And finally, we put them in the level support and measure the length of the tape, which was about 20 centimeters, and the distance between the repulsion that the tapes create, the top and the bottom tapes. This distance allowed us then to find the mass of the tape to then calculate the value of Q, which is the charge that we will find later on the presentation.
When interacting two pieces of charged tapes, we found that they repelled each other, as well as when you overhandle the tape, it can cause it to lose its charge, since we have so much room for the electrons to jump around and move in rather than the pieces of tape. So this, simply put, means the more you touch it, you will ground it. Another thing to keep in mind while doing this is that like charges will repel and opposites will attract, and neutral items can be polarized, which will then allow them to be attracted to a charged object. Above you will see our measurements for the approximate charge of tape A as well as tape B, and that is covered from question 3. We determined the magnitude of the gravitational force and then plugged in our values to get our charge. And then in part 4, we used the answer we got in part 3, plugged that in to find that there was a deficiency of electrons, meaning that the charge is positive. We concluded this from rubbing a balloon on our head, which would mean that the balloon is negatively charged, and then laying down a piece of tape flat on the table and then laying down another piece of tape, ripping up the top layer of tape and holding that charged tape up to the balloon. And we saw that the tape was extremely attracted to the balloon as the tape was attracted to our hands. So this means that opposites attract. So since the balloon is negative, our tape has to be positive. But even if we assume that the tape would be neutral, and if we held it up to a charged balloon, the balloon would polarize the tape and it still would be attracted to the balloon. As seen on the picture to the right, our top tape is showing that it is repelling from the bottom tape, and around 4.8 millimeters is when our top tape started, from where the bottom tape is to the top tape when it starts to repel. And as well for this one, we determined our gravitational force by finding our mass of our tape. And to do this, we took a value that was given to us in our lab handout and took the grams per centimeter value and multiplied it by our value of our tape, the length, which was 20 centimeters, and then we got 0.24 grams, and then converted the grams to kilograms, which was 0.00024 kilograms.
To start off, we know that the length of our tape is 20 centimeters long with the width of 1.9 centimeters. Through our calculations, we found that the mass of the tape is equal to 0.0024 kilograms. We then used our mass to determine the magnitude of the gravitational force on tape B by multiplying our mass and gravity. We know that the gravitational force is 0.02352 kilograms meters per second squared. Being as precise as possible, we measured the separation distance where the tape begins to float. The distance is also represented by r, and it is 48 millimeters. Calculating the charge on the tape requires us to take a measured separation distance and the gravitational force and plug it into the reworked version of Newton's second law. We will then determine the number of electrons on tape B and whether there is an excess or a deficiency, taking our charge, dividing that by 1 elementary charge in coulombs. We know that we have a deficiency in electrons. As we computed the deficient electron on tape B, we then computed the number of atoms on the surface of the tape and plugged it into the denominator to divide the number of electrons on tape B to determine the fraction of what electrons were given or accepted. In conclusion, these calculations were useful in determining the number of atoms on the surface and how the charges transferred between tape A and tape B. This experiment provided physical insight into how the triboelectric effects work. Our results show that both tapes have a positive charge, meaning that they have a deficiency of electrons. The charge of the tape was 2.454 to the 10th of the negative 8th coulombs. The amount of electrons deficiency on tape B was 1.467 times 10 to the 11th. The fraction of the atoms to give up the electron of the tape was 1.544 to the 10th of the negative 5th.